It's okay. I don't need it anyway. All right. So let's talk big picture. Okay? Big picture. Number one, you basically only have 4 possible equations that you can use on anything. Okay? It isn't like there's 1,000 to choose from. You've got V equals V naught plus AT. You've got X equals the average velocity times time. This isn't on your sheet, but sometimes it's handy to have. You have X equals 1/2 AT squared plus V naught time, and you have that equation. Okay? Okay? That's it. So the only thing you can have. Okay, this is it. This is all the bullets you have in the gun. This is it. Now, out of this, you only have a limited number of variables. You have your final velocity, your initial velocity, your acceleration, time, and distance. Okay? That's it. Between these equations and these variables, those are the only things you have in town. Okay? We don't have to worry about mass. We don't have to worry about momentum, energy, anything. This is it. Okay? This is the only thing that can happen. And every problem that you have is only going to be one of 2 things. It's either going to be speeding up or it's going to be slowing down. That's it. So either your acceleration and velocity have the same sign, or your acceleration and velocity have opposite signs. Okay? That's it. Nothing else. Those are the only 2 things that can happen on any problem that you have. So, let's look at, say, for example, let's compare and contrast. I love that term. Questions 4 and 5. Okay? So question 4, you're talking about a large supertanker, okay, that you use to carry large amounts of oil, cargo, drugs, whatever, okay? So this thing is moving at a certain velocity, right? You got to change that into meters per second. And you're going to make this thing slow down, okay? If you ever leave Mays High School or Purgatory High School and you get a job commanding a supertanker, you can't stop these things on a dime, okay? They slow down very, very slowly, okay? So what you should see on number 4 is that you get a very, very, very small acceleration because it takes so long for this thing to stop. Your distance should be about 5,000 meters, which is about 5 kilometers, which is about 2.5 miles. So what that means is if you've got this supertanker traveling at about 16 knots, which isn't all that fast, in other words, if you're going to stop, you have to start slowing this thing down 2.5 miles before you want it to stop, okay? Because it takes so long. So don't wait until you're in the harbor and go, oh, I guess we should try and stop now. No, bad things are going to happen, right? It's incredibly slow acceleration because it has incredibly large mass. Now, you contrast that with what's going to happen on number 5. You have a bullet traveling almost the speed of sound, and you're going to stop it in 5 centimeters, which is about this far. Okay? So the difference being is that on the bullet, you're going incredibly fast, and you're going to stop it in an incredibly short distance. Supertanker, you're not going very fast, but it takes an incredibly long time to stop it. So you have 2 accelerations, but you have vastly different values for those accelerations. Okay? Now, anybody have any specific question you want me to go over? No? Well, may I suggest, let me see your paper, right? No, hold on. Let's talk, here, let me go over some ones that typically give you fits. Okay? Like, let's talk about number 15. Okay? Which is the one from pyrotechnic. So, let's think about number 15. Before you do any math at all on number 15. So, here's your mortar, right? You're going to shoot this thing up in the air. Now, when do you want this thing to explode? Right after it leaves, right before it comes back down, or towards the top of the flight? Probably towards the top of the flight, right?
Right when you light it.
Well,
This one I would want.
yeah, because explosions happen here lead to lawsuits, okay? You want explosions way up here. So on your velocity time graph, you're going to start at 50 meters per second. Okay? That's the velocity that it's to be launched at. So what's this velocity time graph going to do?
Yeah, it starts there and goes down.
I want to just do this.
Yeah.
What's the slope of the line? Negative 9.8 meters per second squared. Now, does it initially have to go from 0 to 50? Yes, but that's something else. We're just going to look at it after it leaves. So, where do you want the explosion to occur on the graph? Here, or somewhere in this region? Somewhere in this region, because that's when it's near maximum height. This is where I want the explosion to occur. Somewhere in this region. Okay? Now, do you know the initial velocity?
Yes.
Do you know when the explosion occurs?
Yes.
Yes. So the first thing you want to find out how high it is. There is only one way that you can do that. And that's use 1/2 AT squared plus V naught time. You know your initial velocity? Okay? The initial velocity is not 0. We're not dropping the pyrotechnic. We're shooting it up out of a cannon. So, you know initial velocity, you know time. Make sure that you use negative 9.8 meters per second squared here for that acceleration. Okay? It has to be negative. Otherwise, you add two positive values together and you get an answer that's way too big. Okay? So, that maximum height on 15 should be around 130. Yes?
Oh, wait, I'll wait.
Okay. Huh? Good. Now, the next thing you want on B is what is the velocity of the mortar at this point? So I'm trying to figure out where this is. Now again, here's the worst thing that you can do, is that you get wrapped up in this equation and the only thing you focus on is an answer. You got to see the forest for the trees. If you look at your velocity time graph, I'm going to give you this time of 5 seconds. What I want is the corresponding velocity that matches with this time. It could be 0, that's a possibility. It could be a negative number, which would indicate that it's on its way down. Or it could be a positive number, which indicates it's on its way up. Okay? But I don't know what it is. But all this is, the only way to work this is just a slope-intercept form. I'm giving you an x value with a known slope and a known y-intercept, and I want to know what the corresponding y value is. That's it. Okay? So if you look at v equaling v naught plus at, you know the initial velocity. Yeah? You know your acceleration. Yeah? You know the time. Yep. Find your final velocity. There you have it. That's it. Boom. There you go. You should see the final velocity is a pretty small number. And it might be positive. I'm just saying. Now, let's talk about number 16. Leroy, Bubba, and Daryl. Okay? This is important that you get this concept. And this boils down to what we talked about yesterday. Okay? And this Jedi Stoffel law. Stop the force and watch. So, here's the center. We'll even draw a visual. So here's the bridge. Okay? And we got Leroy, we got Bubba, and we got Daryl. Okay? Leroy, Bubba, Daryl. So, I tell you that Leroy just drops the ball. Okay? Bubba, always the rebel, throws the ball up with velocity 10 meters per second. So he's going to do this action. And then you have Daryl, and Daryl has anger issues. So Daryl throws the ball down. Daryl's a little pouty. Okay, so he throws the ball down. Okay, all right? Daryl's a pessimist, always has been. Okay, now, let's do the Jedi Stoffel, I think. So let's start with Larry. Larry's got the ball. Is he exerting a force on the ball to hold it? Yes. He stops applying the force, right? What's the initial velocity of the ball? 0. He stops applying the force. What's the only force left acting on the ball? Gravity. So let's start with Larry. So here's the velocity time graph. What's Larry's graph going to look like? Where's it going to start? 0. Where's it going to go? Down and like this, right? What's the slope of the line going to be? Negative 9.8 meters per second squared. Okay? So there's Larry. Good? Okay? Got that. Now, here's Bubba. Okay? Now, Bubba's a little bit more complicated, right? But Bubba is going to start at 0, right? And he's got to exert a force to throw the ball up in the air. But as soon as Bubba stops exerting the force on the ball, so we're going to stop the force exerted by Bubba. As soon as you stop the force exerted by Bubba to throw the ball up in the air at 10 meters per second, what's the only force left in town? Gravity. What acceleration is that gravitational field going to cause? Negative 9.8 meters per second squared. So is the acceleration of the ball thrown by Bubba going to be the exact same as the acceleration of the ball dropped by Larry? Yes. Why? Gravity doesn't go, oh, the ball is going away. It all have a different gravitational field than if the ball was just dropped. So, yes, it creates a uniform acceleration. So if this is Larry, Bubba is going to start up here at 10 meters per second. But what's it going to do? As soon as it leaves his hand, you stop the force, it's going to do what? Think. Right? Is this slope going to be the same as Larry's slope? Yes. Beautiful. Now, Darryl has anger issues. What's Darryl going to do? Darryl's going to throw the ball down. Okay? But again, stop the force. As soon as that ball leaves Darryl's hand, what's the only force acting on it? Gravity. And what's the acceleration caused by gravity? Negative 10 meters per second squared, right? So everybody wants to think, well, the acceleration should be faster if you throw it down. Okay? Once it leaves your hand, whether you throw it down, throw it up, throw it horizontal, shoot it out of a cannon, it doesn't make any difference. Once you stop applying the force, and the only force in town is gravity, what becomes your acceleration? Negative 9.8 meters per second squared. So, Darryl is going to start where? Darryl's going to start down here at negative 10. What's going to happen? What's going to be the slope of all three lines? Negative 9.8 meters per second squared. Because once you stop applying any force to it, and gravity is the only game in town, that becomes your acceleration. Okay? Beautiful. Grand. Okay. Now, let me give you some hints on some of these answers. On 13, and listen to what I tell you on 13, because if 13A is wrong, everything else is wrong. Your answer to 13A should be very close to the legal drinking age. Okay? Not what some of you think it might be after tonight's game. Okay? Close to the legal drinking age in Kansas. Not that any of you do anything like that. Just saying. On number 11, with the cannonball is fired straight up, initial velocity 24. Maximum height on that one should be around 30. Okay? Ish. Around 30. On number 10, which don't think this hasn't happened with physics people, the height of the building should be in the mid-30s. which is actually a pretty tall building.
That is a bridge.
Was it a bridge? Okay, pretty tall bridge. On number 8, with the building, and this is actually how tall my tables are. Both of your answers on number 8 should involve the number 3. Different decimal places, but both of them should involve the number 3. Ashley, are we good? Like those? Okay. Anyway, anything else? We're good? Fantastic. Life's grand. If you need some more time, if you can get this to me just by the end of the day, that's all that really matters. So, but I just need to have it by the end of the day. Okay, so, Lauren, can you stop that for just a second? Now, here's another thing after looking at some of your papers. All of your answers should have at least 3 significant digits. Okay? Right? At least 3 significant digits. When I typed up all of these values, I gave you a minimum of 3 significant digits in every value that I gave you. So let's say that you have an answer of negative 0.008. How many significant digits does this have? It has 1 significant digit. These are zeros. They're freshmen. They're taking up space. This only has 1 significant digit. Bad. So make sure that you have that corrected on your sheet. Okay. So here's kind of a different version of these same equations. So here's what we're going to do. We're going to take a ball. We're going to throw it up in the air, okay, with a certain velocity that I don't know. Because realistically, when you look at how you actually measure things, it's extremely difficult to throw this ball up in the air and get an idea of the velocity. Okay? I really can't do that. Because it's, number one, as soon as it leaves my hand, what does the velocity begin to do? It begins to change. Okay? Measuring acceleration, that's a little dodgy too, because it isn't like, oh, I can have this device that measures acceleration directly. But what's easy to do is to measure time. Okay? So I'm going to throw the ball up and I'm going to time it from when it leaves my hand until it gets back. Okay? So this is, and I can get a pretty good measurement of time. Okay? That's pretty simple. Okay, boom, stop, there we go. So this is the only number that I have, is 2.8 seconds. This is it. But from that one number, I want to calculate the initial velocity at the launch, the velocity when it lands, the maximum height, the velocity and the height at 1 second. I want to draw the position time graph and the velocity time graph from one number. Okay? But there's something else that we know. What else do we know? Yeah, we know the acceleration due to gravity. Okay? Right? It's implied that we know that. And this is assuming that we're on Earth, and we are. Okay? So let's actually kind of work backwards. Let's work kind of up from here. Okay? So what's the position time graph going to look like? Right? So our position time graph, so that was the setup. Let's kind of get rid of that. Okay? So our position time graph is going to go deep. Where's the ball at this point? Right? Velocity is going to be 0. It's going to be at its maximum height. Now, this is important. Since the ball is going to come back down to the exact same height that it was launched, we can assume that the path is symmetrical. Okay? But that only works if it returns back to the same height, which in this case it does. Okay? So if the total flight time is 2.8, that means this has to be occurring where? 1.4. Okay? So this is going to be 1.4 seconds, and this is going to be at 2.8 seconds. Now, let's talk about my velocity time graph. I don't, and you're going, but Mr. Burkhead, we don't know what the initial velocity is. You're right, we don't. We'll get there. But what's my velocity time graph going to look like?
It's going to be a straight line.
Like this?
A straight linear.
like that. Where's the ball going to be at this point? Maximum height, which is going to be at 1.4 seconds. And we know this is going to be out at 2.8. Good so far. Okay? Old school. Nothing new. How is this point going to relate to that point? It's going to be the same number, but opposite signs. Which means this is going to be speed. Okay? They're both going to have the same speed, but they're not going to have the same velocity because the velocity is going to be in opposite directions. So as soon as I find this point, guess what? I know what this point is. Okay? So once I find one, I know the other. So this is basically asking for the same number, but they're going to be opposite signs. Okay? All right, so we got that going for us. Now, before we do any calculations, don't even think about an equation. Don't think about anything else. Is my initial velocity, when I throw this ball up in the air, okay? I think very carefully before you answer this, okay? Is my initial velocity when I throw the ball up in the air going to be less than 9.8, greater than 9.8, or exactly 9.8 meters per second? So I have less than 9.8 meters per second, more than 9.8 meters per second, or exactly 9.8 meters per second. So how many things is going to be less than 9.8? 1. So you're either the lone voice in the desert that's right or the lone voice that's wrong. How about equal to 9.8? Greater than 9.8? Okay, those are your only three options. Only about a third of you voted. Okay.
Is there a don't know option?
There's not a don't know option. Okay, I wish there was that option on the ballot. I don't know who to vote for, and that's what you mark. I'd feel better if you don't know who to vote for, that's what you mark. I don't know. Pick one. I don't know. Okay. What's the slope of this velocity time graph going to be? Negative 9.8 meters per second squared. So for those of you that said that that the velocity was going to be more than 9.8, what was your thought process? What'd you say?
You're applying force to it.
Well, yeah, I'm applying force to that. Okay? I'm applying force to that. Applying force to that. Because I apply force to it, that doesn't mean anything relative to 9.8. Maddie? Say that one more time, just a little bit louder.
The distance, like, from, well, I guess, from your hand to the ice point and ice point down.
Your explanation is beautiful, except you use one wrong term. Okay? It isn't distance. Okay? Because we don't know what the distance is. Okay?
Your initial velocity.
Ah! Okay. Now, we're going to run with your idea. It's a grand idea. Okay? Beautiful insight. Think about this. If you click that one more time, what if my... I want to launch it. Okay? What if... Let's play the what if game. What if my initial velocity had been exactly 9.8? My initial velocity had been exactly 9.8 meters per second. How long would it take to go to 0? Exactly 1 second, right? That's what it would be. Exactly 1 second. Because I would start at 9.8, because this is, you have to remember what the slope represents. It's how much your velocity changes per unit of time, right? So if I start at 9.8, it's going to take me exactly 1 second to go to 0, right? So since it's more than 1 second, so this is where you're right. So it isn't a function of height, it's a function of velocity. The height of this initial velocity is more than 9.8. So I know my initial velocity has to be more than 9.8 meters per second because it took more than a second to reach the maximum height. Okay? Does that make sense? Okay, this is one of the key things that you have to understand. Okay? Understand what this number means. It means that for every second that this ball is in the air, this velocity is changing 9.8 meters per second. And it's either going to make it slow down at 9.8 meters per second, or it's going to make it speed up at 9.8. That's what that number means. Okay? All right. So when we are at maximum height, Maddie, you're rolling with this. When I'm at my maximum height, what's my final velocity going to be? 0. Do I know my acceleration? Yeah, I know my acceleration, so I know the slope of the line. Do I know how much time it takes to get there? 1.4 seconds, right? So here's the deal. Look at this. I know my final velocity is 0. I know my acceleration, negative 9.8 meters per second squared. I know my time. What's the only thing I don't know? I don't know this point. Now, look, Hill. Oh, okay, well that's cool. Because I know V equals V naught plus AT. What's the only thing I don't know? V naught. I know everything else, right? So, Katie, how am I going to get V naught by itself? I get choked up about this too.
Subtract 18
Beautiful. So I'm going to have V minus AT is going to equal V naught. Simple deal, right? Now, this is my final velocity. What's my final velocity? 0. So this is what I've got. I'm going to kind of do the John Madden thing. We're coming up here. Boom. Okay? So I got 0 minus. Now, what's my acceleration? Negative 9.8 meters per second squared. And the time, don't use the 2.8. Don't use the entire time. I got to use the 1.4. So 1.4. So this is why you have to pay attention to signs. I have 0 minus a negative 9.8. So because I'm taking 0 minus a negative number, that makes my initial velocity positive, which matches with why this velocity time graph starts up here. Okay? This is why you have to work this from a holistic standpoint. So here's the short version. Somebody said 1.4 times 9.8.
$13.72.
So we'll call it 13.7 meters per second. Now, let's go with what Maddie said earlier. I said, is the velocity going to be more than 9.8? She goes, yeah, sure, it is. Okay? Check my math, and that's bigger than 9.8. Matches with what we said. Now, here's how you can check that you got this right. Okay? Because you'll see this. If this number is wrong, everything else that you do is wrong. Okay? Everything else is wrong. Set this at 13.7. Set this at 0, 1.4. Find the slope of the line. If the slope of your line is negative 9.8 meters per second squared, guess what? You did it right. If the slope isn't negative 9.8, you did it wrong. Okay? Simple as that. If you take 13.7 and minus 0 and you divide it by 1.4, guess what? You're going to get negative 9.8 meters per second squared, which is what the slope of the line is. So once you get the number, you can very easily verify, oh, hey, I did it right. Find the slope of the line. Okay. So if this is my velocity when I launch it, what's my velocity when it lands?
Negative 13.7.
Negative 13.7. Okay, that's easy. Boom, there we go. Now, find the maximum height. This has an identity crisis. You can find this a whole bunch of different ways. What's one way I can find my maximum height? I could use which equation?
X equals 1/2.
Then,
X equals
No, that equation finds
I was just saying
Hold on.
something.
So let's see with what we know. We know we're at 13.7 meters per second. We know our velocity time graph comes down like this. We know that's 1.4 seconds. We know the acceleration is negative 9.8 meters per second squared.
It's the second one.
So what's one option?
X equals final velocity plus initial velocity divided by 2 times time.
So v plus v naught over 2 times time. Beautiful. Do I know my final velocity? 0. Do I know my initial velocity? Do I know the time?
Yep.
Okay? So I could take 0 plus 13.7 meters per second, divide that by 2, multiply that by 1.4 seconds. Beautiful. What'd you get? 6, around 10 maybe, ish. What'd you get? Room full of calculators.
$9.59.
Not bad. 9.59. Set around 10. Okay. That's one way. How can I use my velocity time graph to find it? Yeah. This looks like a triangle, right? Ah, here's the odd thing. 1/2 base times height, right? Look. You're taking 1/2 times the base, which is 1.4 seconds, times the height, which is 13.7 meters per second. Oh, miracle of miracles. Look. It's the exact same thing that you do over there. You just write it in a different sequence, but it's the exact same math. Guess what? You're going to get an answer of 9.59. Woo! Okay, what's another thing I could do? Could I use that equation? I could. I could go v squared equals v naught squared plus 2ax. So I need to find x, right? So I got v squared minus v naught squared over 2a is going to equal x. Beautiful. Do I know my final velocity? Do I know my initial velocity? Do I know my acceleration? I can find it that way. So I can use that equation. There's another way that I could do it.
X equals 1/2 at squared plus
I could go x equals 1/2 at squared plus v naught time. Do I know my initial velocity, time, I know my acceleration, I can find x that way. So, I don't care, I don't care how you find your maximum height. I don't care. Pick one. Okay? But here's what's important. Every one of these calculations is dependent upon this initial velocity being right. So if you've dinked up this initial velocity, everything is going to be wrong. Okay? So this is why it's so important that you go back and verify that that initial velocity is right, or bad things are going to happen. Okay? Beautiful. All right. So we got the maximum height. What do you say? 9.59 meters. Okay? Now we need to find the velocity and the height at 1 second. Now, here's the deal. This is easy if you think about it. And there's a reason that I particularly chose 1 second. I want to figure out how fast it's going at 1 second. Now, before you do any math at all, is the velocity at 1 second, Jennifer, is the velocity at 1 second going to be a positive or a negative number? Why?
Because it still hasn't changed direction.
How do you know it still hasn't changed direction?
Crossed.
1.4 seconds is when it crosses. And
Yeah, it reaches its maximum height when?
at 1.4.
At 1.4. So at 1 second, it still has to be on its way up, right? So the velocity still has to be positive. True? Okay. It is the simplest calculation in the world. What's the easiest way to find your velocity at the end of 1 second? knowing that it starts at 13.7. What do you have to do? What's the easiest thing? Is the easiest thing to do? What are you going to do? Subtract 9.8. Okay? Subtract 9.8. Because at the end of 1 second, it's going either 9.8 meters per second faster or 9.8 meters per second slower. In this case, I start at 13.7, I subtract 9.8, voila, there's my velocity. There you have it. Now, to get the height at 1 second, the only way you can do this, is if you go over to this equation, this x equals 1/2 at squared plus v naught time. So to find the height at 1 second, the only way you can do that is if you plug numbers into this. Okay? So, what was the velocity at 1 second? Somebody take 13.7 and subtract 9.8 meters per second from it.
3.9.
3.9 seconds. Now, what if I said, what's the velocity at 2 seconds? What would you do? Subtract another 9.8. So somebody take, this is meters per second. Somebody take 3.9 and subtract another 9.8 from it. And I'll show you why I want these numbers in just a
Negative
second.
5.9.
What'd you get? Negative
5.9.
5.9?
9.
Okay? Yeah, that's right. Okay. Now, this is at 1 second, this is at 2 seconds. So here's the deal. I want you to think about this. Why is this number negative at 2 seconds?
Because it's already past.
Yeah, it's reached its highest point and it's on the way down. So somebody remember these numbers, 3.9 and negative 5.9. Okay? I'll show you. I need those numbers in just a second. So I'm going to draw I'm going to go back to this position time graph. Okay? Here's 0, here's 2.8, here's 1.4. Okay? Here's the maximum height, velocity is 0 meters per second. If I came out here at time 0 and drew the tangent line at time 0, what should the slope of that line be? That would be a horizontal line.
13.7.
13.7. Why?
That's
That's my initial velocity. Okay? Now, if I came out here to 1 second, at 1 second and drew the tangent line, what's the slope of that line going to be? 3.9. Why 3.9? Because that's how fast it's going at 1 second. Okay, well that's cool. All right. So that's going to have a slope of 3.9 meters per second. If I came out here to 2 seconds, what's that going to have?
Negative 5.9.
Negative, whatever.
5.9.
That's a horrible line. But negative 5.9?
Yeah.
Okay? So here's the deal. If I ask you, which I'm going to on the test on Tuesday, if I say, hey, what's the slope of the tangent line on a position time graph at a certain value? What am I asking you to find? The instantaneous velocity. So if I ask you the slope for the tangent line, that's code for, oh, how fast is it going at that point? Okay? And this is what you should see. Oh, I'm going from 13.7 to 3.9 to 0 to negative 5.9. Out here, what would the slope of the tangent line be? Negative 13.7. Because now it's landed with that velocity. Got it? Good, Grant? Okay. So, stop that. Okay. So, here's what you've got going on this. This is your last acceleration assignment. So, we're going to start off, got some simple questions, slope of the position time graph, slope of velocity time graph. Those answers should be completely old hat, should not even have to think about those. Now, let's talk about number 4. Okay? So, ball is thrown up in the air and returns 4.4 seconds later. So, all of number 4 is exactly what I just worked, except for instead of having a time of 2.8, it's 4.4. Okay? It's the exact same thing. I want to know the initial velocity, the maximum height, the final velocity of the ball. You're going to draw a position time graph. Now, and on D, on 4D, I say, on a half sheet graph paper, draw the position time graph. What's the slope of the line at 0 seconds? What's the code? What am I asking you for on D1? I'm asking you for the initial velocity of the ball. So your answer to D1 is going to be the same answer that you have on 4A. Now, because if 4A is wrong, literally everything else is going to be wrong. Your answer to 4A should be around the legal drinking age. Okay? If you don't get something around 21, and that's an ish, okay, 21-ish, stop. Because everything that you do from there on out is going to be wrong. Okay? Now, let's turn over to page 2. So then you need to draw a velocity time graph, answer some questions on that. Okay? Now on number 8, let me kind of lay out what's going to happen on number 8. So you have 2 spaceships, Enterprise and Columbia. Enterprise is moving at 450, the Columbia is moving at 600 meters per second. They're at the same place, okay? So imagine that you have the Columbia and you have the Enterprise, okay? They have different velocities. One's moving much faster. But when we start this analysis, they're both at the same point, okay? So there's like, we're looking at them right here. They're at the same point. So what's going to happen is that they're both going to start to slow down. They're going to go out. They're going to stop, and they're going to come back, and they're going to end up back at the same point at a certain amount of time later. So here's what I've got. So Enterprise continues to try to reverse start, slow down, return to the same spot 86 seconds later. Okay? So here's what's going to happen. They're going to be here, they're going to go out, slow down, stop, and they're going to come back, and they're going to reach back at the same point 86 seconds later. Okay? So the time for them to go forward and stop is the same. Okay? I'm not saying they're going to go the same distance. What I'm telling you is that they're both going to go from here to 0 at the same time, and they're going to get back to 0 at the same time. The distances might be different, but the times and locations to get back to this point are the same. Okay? So they're here, they're going to go forward, they're going to get back, both at 86 seconds later. Okay? That's the setup. Are they both going to accelerate?
Yes.
Do you think they're going to accelerate at the same rate?
No.
Why?
Because
They're different velocities.
Yeah, they're going at different velocities, but the times are going to be the same. So they're going to have completely different acceleration rates. So, on A, I want the acceleration of the Enterprise, the acceleration of the Columbia. Then I want to draw a velocity time graph showing the motion of each ship on the same graph. Make sure when you get to 8C that you label which one is which. Okay? Just don't randomly draw lines on a graph. I want to make sure I know which one is which. If you want to do one in pen, one in pencil, one colored, one's dashed line, I don't care what. Okay? Just so I know which one's which. On number 9. Okay? Now, let's talk about number 9, because you got to visualize what's happening on number 9. So imagine this is a model rocket. Okay? I'm going to launch this thing straight up in the air, and I tell you that it's going 75 meters per second at a height of 30 meters above the ground. So visualize this. The rocket's going to start here. We're going to fire it up, okay? And when it is 30 meters above the ground, which is pretty good height, like this ceiling is about 2.5, okay? So we know when it's at 30 meters high, it's going 70-something meters per second. Do you know an initial velocity?
yes.
Do you know a final velocity? Do you know a distance? What can you find? Everything. You can find acceleration, you can find time. There's a whole bunch of things that you can find. Okay? Now, and then you're going to draw a motion diagram showing velocity vectors and acceleration vectors. If you want to do this off to the left, you can. If you want to do it on another sheet of paper, that's cool. Now, here's the whole kicker on number 9. At that point, we're going to shut off the engines. Okay? So this is this Jedi Stoffelwalk concept. So it's like me throwing this ball up in the air. As soon as that ball leaves my hand, that's like shutting off the engines. Okay? So as soon as I shut off the engines, or as soon as it leaves my hand, I stop applying a force. As soon as I stop applying the force from my hand, what's the only force left in town? Gravity, which is going to create an acceleration of negative 9.8 meters per second squared. Okay? Because I shut off the force, I shut off the engines, gravity is the only game in town. And it's going to make it slow down. So, and that's the hint that I give you. So, how long will it take to reach the maximum height from the time the engine shut off? Draw a motion diagram showing the two velocity vectors and an acceleration vector after I shut off the engine. So there's that. Now, there's a small little lab that you need to do. Okay? The lab won't take very long. The mini lab on page 3, here's what I want you to do. You're going to try and calculate an experimental value of gravitational acceleration. Okay? So on page 3, and I tell you this in big bold letters, do not use negative 9.8 meters per second squared on the mini lab. Okay? You can use it on the other calculations. Do not use negative 9.8. You're trying to find an experimental value of acceleration due to gravity. Okay? You can use it on page 1 and 2, you just can't use it on page 3. So here's the technique that you're going to do. It's the exact same idea of what you did with the car lab, where it rolled up and it rolled back down, only this time we're just going to have the full effect of gravity. So you're going to take a tennis ball or a golf ball, and what we're going to do is we're going to bounce it, okay? So you're going to bounce it, and you got to have it come all the way back down, but not hit the ceiling. So there's a technique. Ooh, that was a good one. Okay, so what you're going to do is you're going to time it from the time that it hits the ground until the time that it gets back down. So you're going to go bounce to bounce. Now, the other thing that's tricky is that you have to record the maximum height of the ball. Okay? So you got to have somebody watching how high it is. Right?
Bounce it as high as your head and then measure how tall you are.
Well, you can if you can get it exactly to the height of your head. Okay? But the farther it goes, like less room for error that you have. Okay? So what you're going to do is you're going to time it from here, boom, and you're going to measure how high it is at that maximum height. That's all the data that you need. Okay, that's it. And you can do everything from that. Now, on this, I cannot emphasize this enough. This is kind of like your lab final for this acceleration unit. You show me every calculation. If there are numbers that have no units, at that point, literally, listen to me. If I see any numbers that don't have units on them, or I don't know what you've done, at that point, I will immediately stop grading your paper. I'm just going to stop. Okay? As soon as I see that, I'm done. Okay? I have better things to do with my time than to sort through a bunch of random numbers that don't mean anything. This is a lab. You're trying to show me, hey, Burkamp, these are the things that I've learned for the past 6 days. Okay? Literally, mark my words. I'm telling you now, and it's on tape. And I will go back and play this for you. So then you go, oh, but you didn't tell us. Yes, I did. Okay? I see one number or one calculation that doesn't have units on it, I stop. Right then, right there. Okay? Just so everybody's clear. All right, I'm done. Go, be free. I can get the data from the lab first.